So in this lecture, we are going to learn about the constant optimization. Okay, till now we are seeing that we are using the derivative for a single equations. Just we are find the minimum and maximum value. So if for optimizations, if we have some constant, then what happen in such case? So let's just write down. So we are actually going to maximize some functions or some minimize functions. We are simply in optimizations. In finally, just we are going to maximum or minimum for a functions, and the maximum x is called the x star. That is our arc mean of. That is, if you simple this called the arc max or simple arc function. Okay, just if you remember the principal component analysis, just remember the principal component analysis. So what in the principal component analysis, what is our optimization problem? Just if you forgot, please search on Google or just find it. Easily find on any mathematics book. Okay, so the equations is the optimization equations for the principal component analysis is we have to find the optimal u. That equations is 1 by n, I is equals to 1 to n, where n is the number of data points in our training set, u transpose xi whole square. This is our optimization problem in principal component analysis. And one thing, we have one condition such that u transpose u is equals to 1. This part is called the constant part of our equations. Okay, this part is called the constant part. Okay, this part is called the constant. Now we are just simply convert this equation. Just assume we are simply just compare these equations with these equations. That is max of x, f of x, such that here we are taking this function for another functions. Here just simply we are comparing these functions. We are simple here. We are comparing this function through our f of x, and we are comparing these functions through some functions. Let's call it is a g of x is equals to simply some constant, this one. We are comparing this function to g of x. Simple, we are just converted this formula in general form. Okay, now if we just write down this equation in general form, so our general constant form. So general constant optimization will be what? Will be simply we are just read down these equations now. Will maximum of x, f of x, such that g of x is equals to some constant c. So this portion we call the our objective function. Okay, and they have another kind of constants as that equals to c, and let's call another kind of constant, this is equals to d. Let's take, and this portion is called the our constant portion. Okay, this is our optimization portion of that is called optimization function. This is our constant function, and this constant function that is taking the equal sign. This constant is called the equality constant. Okay? Equality constant, and this type of constant is called the inequality constant. inequality constant. Okay, simple, instead of constant I am using here const. Simple, just don't be confused. And anyone can ask me, does there have another kind of constant that we call h of x if less than is equals to, let's take e. Simply, if we have this function, then simply we convert these functions in this form by simply using the multiplication both sides by minus, just simply using the minus sign both sides of these equations. So these equations now coming to this portion. So this form or this form, both are the similar form. Both are the similar. So simple, I am just using this formula here. I am not taking here this type of both, since both are the same form. So since this is our general form of our optimization problem. Now the main thing is that how to solve this optimization problem, how to solve this constant optimization problem. So here simply we are using the Lagrange's multiplier. Simply here we are using here Lagrange's multiplier. Lagrangian multiplier. Okay, simple, here we are using the Lagrangian multiplier. So now the concept is, what is Lagrangian multiplier? So just first rewrite this side, just read, we are just rewrite this equation this side. So our optimal x is equals to x star, simply that is maximum of f of x. This is our optimization function, that is our simply objective function, sorry, objective functions, and our constant is this guy. As that g of x is equals to c, and our h of x greater than is equals to b. Simple, this is our optimization, constant optimization. Now I am going to convert in using the Lagrangian multiplier. So we are calling the Lagrangian multiplier as L. Just simply first we are taking the our objective function, that is f of x, minus, here we are multiply some constant that is called lambda into g of x minus c, and minus mu, and it is called d minus h of x. Okay, here this term, you can easily see that these functions, here variable is, for h functions, here variable is x. Actually we are have to find the optimal x, so this function is variable of x, and also here we are taking two parameters, two constants parameters, that is lambda and mu also. So such that these Lagrangian functions will be the function of x, lambda and mu. Okay, so this is our Lagrangian, this is our Lagrangian function. This function we call the Lagrangian function. Okay, and this mu, and this mu, just another, this mu and lambda, this lambda and this mu is called the Lagrangian multiplier. Lagrangian, simple, just Lagrangian multiplier. And the condition is that the Lagrangian multiplier should be greater than equals to 0. So the simple, this constant optimization problem with the help of Lagrangian multipliers, with the help of Lagrangian multiplier, we are now just convert this optimization problem in a single equation optimization problem. Okay, so just I am not coming to the proof, the solutions of these equations solutions of this equation is the same solutions of these equations. Okay, so I'm not coming to the proof. If you are interested, please find it easily, search it on Google, it will easily find it. So it is not an hard task. I'm not just coming to this part. Okay. So this is the fault. So how to solve? So simply this constant problem, now I'm converting to this constant problem into a single equations. Now as usual, we are now as usual we are now solving this equation. So here it is a functions, L is a functions of three variables. So here we are now using the partial derivative concept that we are learned in previous lecture. So our del L by del x equals to 0, del L by del lambda equals to 0, and what our next variable, del L by del mu is also equals to 0. Now we have to solve these three portions. Now we have to solve these three problems, these three equations to find our optimal solution. So let's take after solving these three equations, we are finding our optimal value for x is x tilde, and optimal value for lambda is lambda tilde, and mu is mu tilde. Okay, these are the same as our x, this x and this x are both the same. So our x star is equals to same as our x. Okay, I'm not coming to this theory portion. Just if you're interested to prove this equation, just find it. You just Google search it, you can easily find it. Okay, just I think you are all understands what is Lagrange multiplier and how it's work on a constant optimization problem. Okay, now just now we are going to apply this constant, this Lagrange multiplier constant in the PCA equations, where this is our PCA equations. Now I'm just coming to apply the Lagrange multiplier concept in this PCA equation. So let's see. So first read down what is our PCA equation. So the PCA equations is max of u 1 by n summation I is equals to 1 to n, where n is our number of data points in our training data, u transpose xi a whole square. Okay, as that u transpose u is equals to 1. If you just simple doing some simple algebra, then you are coming to this equation, just simple doing some algebra. So after simple doing some algebra, we are coming u transpose su. Now I am just going to discuss what is u, what is s. Don't be confused about this u. This u is the same of this u. Okay, this u is the same of this u, but what is x? I'm coming to it as that u transpose u is equals to 1, and now our s is equals to 1 by n summation I is equals to 1 to n xi to xi transpose. Okay, xi transpose. Okay, so this u, this s is the simple, this is just you are simple doing some primary simple algebra, then you are just reaching this equation. So it is not a hard task. Okay, so this is, if you just remember our covariance matrix, it is the simple definitions of our covariance matrix. It is nothing, this is our covariance matrix. This is our covariance matrix. Okay, and this matrix when you see this simple, just type in Google covariance matrix, then you can easily find this equation. So in general that this covariance matrix is denoted as X. So here simple, in PCA we are denoted with X. That don't be confused about X and S. Both are the same here. In the solutions of the PCA, here we are instead of X, here we are using S. Okay. Some books are written in X. Here just here for simplicity I am using S here. Now what will be the final equations after doing some primary algebra? We are reaching this equation. Just write down first. So what is our now PCA equations? So now PCA equations is, now our PCA equations is, just write down it clearly. Then I am going to solve it. Is U as that U transpose U is equals to 1 when S is equals to 1 by n, summed value of 1 to I is equals to 1 to n xi transpose. Okay, this is our S. So this is our simple constant equations of the PCA. Now here we are using the Laplace transform. So let's use. Here we have single constant, so we have to use a single variable, single parameter. For example, here our variable is X. Let's take, we are using parameter lambda is equals to U transpose S U minus our Lagrangian multiplier. Here we have taken our lambda and U transpose U minus 1. Okay, this is our simple Lagrangian what it is, this is our simple Lagrangian function. This is our simply a Lagrangian function in PCA. This is the thing of PCA, and this is our Lagrangian multiplier of PCA. Okay. Okay. So let's derivative it. So first dl by, we are now just first going to derivative with respect to u. So what will be the derivative, and now we are comparing to optimize these equations, so we compare it to 0. So what will be the derivative of u? So simply this will be 2su minus this portion lambda, so simply just 2 lambda u minus this portion will be 0, which equals to 0. Simple, these equations will arise, su minus lambda u which equals to 0. Simply su is equals to lambda u. Okay, su is equals to lambda u. Now if you see these equations, if you simply, here it is not important to find, simply we are avoiding the derivative term to find the lambda value here. So because here optimal lambda is not so important, because what, because finding this optimal value, this value is not important, is not so important. So simply we are ignore it. Simply we are ignore this term. Ignore this. Simple, here we are ignoring this term. Now simple, here we are interested to find the optimal W. Okay? U star. Mainly we are interested in U. So simple, we are reaching these equations. Now if you just remember the eigenvalue and eigenvector, suppose we have a matrix A, and if you just remember eigenvalue and eigenvector, how to find the eigenvalue and eigenvector of a matrix, then you simply see these equations: A is equals to lambda u. Then u is called the u is called the eigenvector of the matrix A, and lambda is called the eigenvalue of this matrix A. This is eigenvalue of A, and this u is the eigenvector of A. Okay. Now we are just simply compare this concept with this concept, with this equation. Simply I am just compare this to this. Okay. Just compare both these equations. So what will be the situations now arise? So now what? Now u is the our eigenvector. U is the eigenvector of our covariance matrix A, and the lambda is the simply eigenvalue of our covariance matrix. Okay. So in the, if you just remember our PCA, then simply we are reaching the solutions direct. Here we are reaching the solutions. Our solutions is the, so our to find our optimal features vector, we are finding the eigenvalue of our covariance matrix. So simple, the solution is that. So simply here we are using the Lagrangian multipliers and the derivative concept, we are finding these solutions of our principal component when managed. The proof of the solution is this. Okay. So the proof of this principal component analysis is this. Okay. This is our proof of PCA. So simple, if you just recall the PCA, principal component analysis, if you just recall it, in what we find in principal component analysis, we find that our optimal features vector is simply the eigenvalue, the eigenvector of our covariance matrix. Okay, simply. So how to find this? This is the main solutions of this PCA. Okay, I think this lecture is all about clear, and now you are all confused. To reduce your confused to from PCA, and why PCA using the eigenvalue and eigenvector to finding the optimal features. So this is its proof. Okay, I think it is clear all of you. If you have any problem, please comment below.